Welcome everyone to Dimebar High's third astronomy podcast. I'm your host, Brandon, and I'm here with my co-host, Ayaan. Today we are diving into some of the most profound concepts in physics and astronomy, relativity and time dilation.
Thanks, Brandon. These ideas can seem a little abstract, but they're foundational, changing our understanding of the universe from the basics of motion to the incredible behavior of objects near massive black holes. While time may seem like a steady, unchanging backdrop in our daily lives, relativity reveals that it's deeply interconnected with space and can stretch, compress, and warp in many surprising ways.
In this exploration, we'll cover the history of relativity, break down time dilation, and dive into how these ideas play out in the vast, mysterious theater of space. Let's start with a bit of background. Before Einstein came along, our understanding of physics was mostly shaped by Sir Isaac Newton. Back in the 17th century, Newton established laws of motion and universal gravitation, which describe the behavior of objects on Earth and in space.
Newton's laws gave us a predictable, almost clockwork universe. Time, for example, was considered absolute. In other words, it was believed that time ticked at the same rate everywhere, for everyone regardless of motion or location.
But all that changed in 1905 when Albert Einstein published his special theory of relativity. Einstein's ideas revolutionized physics by introducing the concept that time is actually relative, meaning it can vary based on an object's speed and gravitational environment.
Right, and Einstein introduced the idea of space-time, a four-dimensional fabric where space and time are interconnected. This was a radical departure from the Newtonian view and helped lay the groundwork for understanding how gravity and motion influence the fabric of the universe.
Finally, in 1915, Einstein expanded his theory with the general theory of relativity, which explained how gravity could warp this space-time fabric. In essence, massive objects, like planets and stars, create curves or dips in space-time. Other objects then fall into these dips, which we perceive as the force of gravity.
Alright, let's dive deeper into special relativity. One of its central ideas is the concept of frames of reference, which describes how observers perceive motion and time differently depending on how they are moving relative to each other.
An example that often helps is the idea of a train. Imagine you're on a train moving at a constant speed in a straight line, with the blinds down so you can't see outside. Inside the train, everything feels normal, objects fall straight down, and you don't feel like you're moving at all.
Exactly. From your perspective, it would be impossible to tell if the train is moving or stationary without looking outside. This is because the laws of physics remain the same within that frame of reference.
This is one part of special relativity, that the laws of physics are identical for all observers moving at a constant speed in a straight line. But here's where it gets really interesting. Einstein proposed that the speed of light is constant regardless of an observer's motion.
Imagine a scenario. Let's say you're on a spaceship moving at 99% the speed of light, and you shine a laser beam forward. Now, classical intuition might lead you to think that the light would travel at 99% the speed of light plus the speed of light. But that's not what happens.
Exactly. No matter how fast you are moving, the speed of light remains constant at about 300,000 kilometers per second. This consistency of light speed led Einstein to conclude that space and time have to adjust to make sure that light speed always stays the same.
This is where we get time dilation. Time dilation is the idea that time passes more slowly for objects moving close to the speed of light compared to those at rest. So if you were on a spaceship traveling at near light speed, you would experience time at a slower rate than someone on Earth.
A famous thought experiment that demonstrates this is the twin paradox. Imagine twins, Alice and Bob. Alice stays on Earth while Bob sets off on a spaceship traveling close to the speed of light. When he returns, he finds that Alice has aged more than he has.
That's because, from Alice's perspective, time was passing normally. But for Bob, moving at such high speeds, time effectively slowed down due to time dilation. This difference in the passage of time due to relative motion is what we mean by time dilation.
Now, you might be wondering where the paradox part comes in. If you think about it, from Bob's perspective, Alice is the one who appears to be moving away from him, so time should pass more slowly for her. If the two twins are observing each other as moving, then each should see each other as aging slower, according to time dilation. In that case, shouldn't that result in a situation where both twins would be younger than the other when they meet again?
Good question. When Bob turns around to come back to see Alice, he breaks the symmetry. In that moment, Bob effectively switches to a different frame of reference, and this acceleration is what distinguishes his experience from Alice's. From Bob's perspective on the return journey, he now sees Alice's clock running much faster than his own. This is because during his acceleration and the return phase, relativity dictates that he experiences time dilation differently due to his changing velocity and direction. By the time he returns, Alice has aged significantly more than he has.
Experiments with atomic clocks on planes have confirmed this effect. Clocks on fast-moving planes tick slightly slower than clocks on the ground. And, in 2015, when astronaut Scott Kelly spent a year on the International Space Station, he actually aged a bit slower than his twin brother Mark, who stayed on Earth.
Now let's move on to general relativity and gravitational time dilation. While special relativity deals with objects moving at high speeds, general relativity explains how gravity itself affects the flow of time.
To expand upon your idea, massive objects, like Earth or a star, create curves or warps in the fabric of space-time. This distortion affects the passage of time. The stronger the gravitational field, the more space-time stretches, and the slower time passes.
One way to picture this is to imagine space-time as a rubber sheet. If you place a heavy ball in the center of the sheet, it creates a dip. Smaller objects rolling across the sheet will naturally fall toward the dip. That quote-unquote fall is what we perceive as gravity.
And this warping doesn't just affect space, it affects time as well. Close to a massive object, time actually passes more slowly than it does farther away. This is called gravitational time dilation.
Black holes provide an extreme example of gravitational time dilation. Black holes have such intense gravity that time appears to slow down dramatically near them. To an outside observer, it would seem as if time practically stops at the event horizon, the boundary around a black hole beyond which nothing can escape.
If you were watching an astronaut fall towards a black hole, you would see them slow down more and more as they got closer to the event horizon, eventually appearing to freeze in place, though they would continue to move from their own perspective.
This effect is also seen with light, resulting in something called gravitational redshift. Light escaping a strong gravitational field, like near a black hole, stretches toward the red end of the spectrum. It loses energy, which is interpreted as a shift in wavelength.
Gravitational redshift also provides us with a way to observe the effects of general relativity. When we see light from distant stars or galaxies, gravitational redshift helps us estimate the gravitational influence of nearby objects, giving us insights into the distribution of mass in the universe. This is different from the Doppler effect, which is actually the main cause of red and blue shift. The Doppler effect has a much more significant effect on redshift and blue shift, because it is directly related to relative velocity between the light source and the observer.
One of the most famous examples of time dilation in action is the twin paradox, which we discussed earlier. But we see time dilation effects with particles as well. Particles moving at high speeds in particle accelerators actually, quote-unquote, live longer than they would at rest.
Another fascinating application is pulsars, which are basically rapidly spinning neutron stars. These stars emit regular pulses of radiation that can be affected by nearby massive objects, altering the pulse frequency due to gravitational time dilation. By observing these pulsars, we can study extreme gravitational fields.
Gravitational waves are another mind-blowing application of general relativity. In 2015, scientists detected these ripples in space-time caused by colliding black holes. Observing gravitational waves helps us study events that would otherwise be invisible, like black hole mergers.
These theories also have real-world applications that we use every day. Take GPS satellites, for example. These satellites orbit Earth at high speeds and are farther from Earth's gravitational pull, which means their clocks tick slightly faster than the clocks on the ground.
This is due to both their speed and weaker gravitational influence, so engineers have to account for relativity in GPS technology. Without these adjustments, our GPS systems would drift off by about 10 kilometers every day.
And then there's a redshift of distant galaxies. Observing redshift helps astronomers understand the expansion of the universe. The farther a galaxy is from us, the more its light is redshifted, which indicates it is moving away from us, evidence of an expanding universe.
Even black holes give us clues about time dilation. When we observe objects near black holes, we see gravitational redshift and time dilation effects that match Einstein's predictions, confirming these ideas in some of the universe's most extreme environments.
So in wrapping up, relativity and time dilation aren't just theoretical concepts. They reshape our understanding of the universe. They impact everything from the way we see black holes to how we navigate on Earth using GPS.
Exactly, Brandon. Einstein's theories have not only given us a new lens to view the cosmos, but have also provided tools that impact our daily lives. They allow us to peer into the past, understand distant galaxies, and even predict the future course of the universe.
Thank you for tuning in to our monthly podcast. We hope you enjoyed this exploration of relativity and time dilation. Join us next time as we continue to uncover the various different topics in astronomy.